Hi everyone! Today we're doing notes for 8.5, testing mu1 minus mu2 and p1 minus p2. So we're going to start with testing mu1 minus mu2 and both sigma 1 and sigma 2 are known. Now just as in the past, because we know sigma 1 and sigma 2, this means we're going to use a z-test. So this will be a 2-sample z-test. Our requirements: let sigma 1 and sigma 2 be the known population standard deviations of populations 1 and 2. Obtain 2 independent random samples from populations 1 and 2 where x1 bar and x2 bar are sample means from populations 1 and 2, n1 and n2 are sample sizes from populations 1 and 2. If you can assume that both population distributions 1 and 2 are normal, then any sample sizes n1 and n2 will work. If you cannot assume this, then use sample sizes n1 greater than or equal to 30 and n2 greater than or equal to 30. So our procedure is going to remain the same. First, in the context of the application, we're going to state the null and alternate hypotheses and set the level of significance. It's customary to use the null hypothesis mu1 minus mu2 equals 0. Now, you can write it this way, or I prefer if we do h0 equals mu1 equals mu2. You can actually use either format. So you can see down below the left-tailed test, our null hypothesis is mu1 is equal to mu2, and our alternate hypothesis is going to be mu1 is less than mu2. For a right-tailed test, null hypothesis is the same, mu1 equals mu2. Alternate hypothesis is mu1 is greater than mu2. And then for a two-tailed test, again, the null hypothesis is still mu1 is equal to mu2, but this time our alternate hypothesis is mu1 is not equal to mu2. Now again, you can use the format referencing 0, or you can use a format where the two groups reference each other. Again, I think it's easier if we just set the first mu equal to the second, or reference them as less than, greater than, or not equal to for the alternate, because this is also the same format that the calculator will use. All right, so we're going to put everything together to get our sample test statistic. So in this case, we are going to have z, and our formula is x1 bar minus x2 bar, and I would recommend in your calculator putting that in parentheses, divided by the square root of sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. Then we use the standard normal distribution and our type of test to find the p-value. Then we conclude the test. Again, the rules are the same. If p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis. And then we interpret our conclusion in the context of the application. All right, so here's our first example. A Michigan study concerning preference for outdoor activities used a questionnaire with a 6-point Likert type response, in which 1 designated not important and 6 designated extremely important. A random sample of N1, I forgot to give you the number. Let's do N1 is equal to 46. So N1 equals 46 adults were asked about fishing as an outdoor activity. The mean response was X1 bar equals 4.9. Another random sample of N2 equals 51 adults were asked about camping as an outdoor activity. For this group, the mean response was X2 bar equals 4.3. From previous studies, it's known that sigma 1 is 1.5 and sigma 2 is 1.2. Does this indicate a difference either way regarding preference for camping versus preference for fishing as an outdoor activity? Use a 5% level of significance. Note, a Likert scale usually has to do with approval of or agreement with a statement in a questionnaire. For example, respondents are asked to indicate whether they strongly agree, disagree, or strongly disagree with the statement. So let's go through and highlight all of our important pieces of information. So from our first group, we have N1 is 46, we have our X1 bar is 4.9, and our sigma 1 is 1.5. From our second group, we have that N2 is 51, X2 bar is 4.3, and sigma 2 is 1.2. We also have important information. They say, does this indicate a difference either way? And we have 5% level of significance. So let's start with writing our hypotheses. Our null hypothesis is going to be mu1 is equal to mu2. Our alternate hypothesis, it says indicate a difference either way. So this is mu1 is not equal to mu2. And then we have our alpha is 0.05. Our next step is we have to find the test statistics. So our formula is z is equal to x1 bar minus x2 bar divided by square root of sigma 1 squared over n1 plus sigma 2 squared over n2. All right, so if we plug all this in, we have 4.9 minus 4.3 divided by square root of 1.5 squared divided by 46 plus 1.2 squared divided by 51. So if we calculate this, again, don't forget, put your numerator in parentheses to make sure you punched it in correctly. And this comes out to be 2.16. So now if we want to find the p-value, we're going to do p-value is normal, CDF. And again, this is a positive z-value, and we're looking for the tail area. So I'm going to do 2.16 up to 10,000, comma 0, comma 1. And when we plug this in, we get 0.0154. Now, keep in mind, this is a two-tailed test. So because this is not equal to, and it's a two-tailed test, we have to make sure that we multiply by 2. Again, we're multiplying by 2 because it's a two-tailed test, and we're doing this by hand. So once we do that, this is going to give us a p-value of 0.0308. Our next step is to compare the p-value to alpha. So our p-value is 0.0308. Alpha is 0.05. In this case, our p-value is less than or equal to alpha. So I want you to decide, would you reject or fail to reject the null hypothesis and make your conclusion? Go ahead and take a moment. In this case, we would reject the null hypothesis. And so we would say we have enough evidence to conclude there is a difference between preference for outdoor activity. Now, if you are going to use the calculator for this one, what we would do is we would choose the 2 sample z-test. And then on your calculator, we're going to go through and enter everything. So 2 sample z-test. First, we have our sigma 1, which is 1.5. Our sigma 2 is 1.2. Then we have our x1 bar, which is 4.9. Then our n1, which is 46. Then our x2 bar, which is 4.3. N2, which is 51. And then we're going to choose mu1. And again, we have not equal to mu2. And then when you go down to calculate, you'll see the calculator does the multiplying by 2 for you for the p-value. So we end up getting the same z-value, 2.16, and the same p-value, which will give us the same conclusion. Okay, next we're going to test mu1 minus mu2 when both sigma 1 and sigma 2 are unknown. Now, when they're unknown, that means we're going to use S1 and S2, the sample standard deviations. So we're going to use a 2 sample t-test. Everything starts similar. We have 2 independent random samples from populations 1 and 2, where x1 bar and x2 bar are sample means from populations 1 and 2. S1 and S2 are sample standard deviations from the populations, and N1 and N2 are sample sizes from the populations. If you can assume that both population distributions 1 and 2 are normal, or at least mound shape and symmetric, then any sample size will work. If you cannot assume this, then both sample sizes N1 and N2 should be greater than or equal to 30. Again, we start with null and alternate hypotheses, and these look exactly the same for the t-test as they do for the z-test. Again, we're going to reference each other. Mu1 is equal to mu2 instead of referencing 0. Our formula for the t-test statistic looks just about exactly the same as the z. Again, the only difference is now we're using the sample standard deviations, S1 and S2. Again, let's put that numerator in parentheses. If you are doing this by hand, the degrees of freedom that you'll use is the smaller of N1 minus 1 and N2 minus 1. When we get our t-test statistic, then we're going to find the p-value. When you're finding the p-value by hand for the t distribution, so again, by hand with the formula, you're then going to use t CDF, and then you're going to put in the lower bound, the upper bound, and the degrees of freedom. Once you have the p-value, again, compare to alpha, choose to reject or fail to reject the null hypothesis, and then interpret your conclusion. So here's our example. 2 populations have mound-shaped symmetric distributions. A random sample of 16 measurements from the first population had a sample mean of 20 with sample standard deviation 2. An independent random sample of 21 measurements from the second population had a sample mean of 19 with sample standard deviation 3. Test the claim that the population mean of the first population exceeds that of the second. Use a 5% level of significance. So let's highlight. So we have a random sample of 16 from the first population. Sample mean of 20, sample standard deviation 2. Our second group is a sample of 21 from the second population. Sample mean of 19, sample standard deviation 3. And we're testing the claim that the population mean of the first population exceeds that of the second. And we have a 5% level of significance. So start with writing our hypotheses. Our null hypothesis, mu1 is equal to mu2. Our alternate hypothesis, it says the population mean of the first population exceeds that of the second. So that's going to be mu1 is greater than mu2. Our alpha is 0.05. Okay, so now we're going to find our value for the test statistics. So using our formula, we have our t is equal to, this is x1 bar minus x2 bar divided by square root of s1 squared over n1 plus s2 squared over n2. And so if we're plugging this in, we have 20 minus 19 divided by square root of 2 squared divided by 16 plus 3 squared divided by 21. The alternative, if you're choosing to use the calculator, would be you're going to choose the 2 sample t-test, and then if you're plugging everything in here, you're going to have your x1 bar is going to be 20, then your sx1 is 2, n1 is 16, then x2 bar is going to be 19, sx2 is going to be 3, and n2 is going to be 21. Then we have our mu1 is greater than mu2. For pooled, you always choose no. So go ahead, choose whichever way you prefer, the formula or the calculator, and I want you to find the t-test statistic and your p-value. Okay, for the t-test statistic, you should get 1.21. If we're doing the p-value by hand, then remember we said we're going to do t-CDF. This is a positive t-value, so we're going to do 1.21 up to 10,000. And then degrees of freedom, remember, is the smaller sample size. We take one less than that, so this will be 15. And so for your p-value, you get 0.1225. Now, if you did this in the calculator, you get the exact same t-test statistic, but your p-value is going to be 0.1165 if you're doing this in the calculator test, okay? So again, either one is fine. You just have to show me the work that matches your method. Okay, once we have the p-value, we can compare this to alpha. So our p-value, I'm going to use the formula one for now, 0.1225 compared to 0.05, which is alpha. Our p-value is greater than alpha. Notice either p-value is, you'll get the same result, either the calculator test or by hand using t-CDF. Because our p-value is greater than alpha, we fail to reject the null hypothesis, which means we do not have enough evidence to conclude the population mean of the first population exceeds that of the second. Okay, we have one more example today, and we're going to go over how to test P1 minus P2. So this is going to be the two proportion z-test. So consider two binomial probability distributions. Each of them has an n, which is the number of trials, r, which is the number of successes, p, which is the population probability of success on each trial, and then p hat, which is going to be r divided by n for each of the two groups. Number of trials should be sufficiently large so that all four n times p and n times 1 minus p are greater than 5. So we start with, in the context of the application, doing null and alternate hypotheses and set the level of significance. Again, we're going to set these equal. In this case, it'll be P1 is equal to P2. When we're testing for proportions, we use P instead of mu. Then they give us what's called a pooled best estimate for the population probabilities of success and failure. So we have this formula for P bar. It's R1 plus R2 divided by N1 plus N2. And then we have our Q bar is 1 minus P bar, or 1 minus the R1 plus R2 divided by N1 plus N2. And you use the P bar and Q bar to get the formula for the z-test statistic, and that's right here. So to get that formula, it's P1 hat minus P2 hat. Again, I'm going to put that in parentheses, divided by the square root of P bar times Q bar divided by N1 plus P bar times Q bar divided by N2. See our normal distribution, so our normal CDF to get the p-value. We conclude, as usual, comparing p-value to alpha and then interpret our conclusion. So it says, the Macek County clerk wishes to improve voter registration. One method under consideration is to send reminders in the mail to all citizens in the county who are eligible to register. As part of a pilot study to determine if this method will actually improve voter registration, a random sample of 1,250 potential voters was taken. Then this sample was randomly divided into two groups. Group 1, there were 625 people in this group. No reminders to register were sent to them. The number of potential voters from this group who registered was 295. Group 2, this group also contained 625 people. Reminders were sent in the mail to each member in the group, and the number who registered to vote was 350. The county clerk claims that the proportion of people who registered was slightly greater in Group 2. On the basis of this claim, the clerk recommends that the project be funded for the entire population of Massac County. Use a 5% level of significance to test the claim that the proportion of potential voters who registered was greater in Group 2, the group that received reminders. So again, let's look at our important pieces of information. From Group 1, there were 625 people, so N1 is 625. And the number that registered, so our R1 is 295. For the second group, we have that there were, again, 625, so N2 is 625. The number who registered was 350, so R2 is 350. Some important keywords, we have that we want to test the claim that the proportion of potential voters who registered was greater in Group 2, and it says use a 5% level of significance. I want you to start by writing the hypotheses. Okay, our null hypothesis is going to be P1 is equal to P2. Our alternate hypothesis is going to be P1 is less than P2. And we're going to use alpha is equal to 0.05. Now, if we're doing this by hand, we need to figure out our P1 hat, our P2 hat, our P bar, and Q bar. So I'm going to do some of this work up top here. P1 hat is going to be R1 divided by N1. So this is 295 divided by 625, which gives us 0.472. Our P2 hat is going to be R2 divided by N2. And so this is 350 divided by 625, which is 0.56. Last, we need to find our P bar and Q bar. So P bar is our R1 plus R2 divided by N1 plus N2. And so this is 295 plus 350 divided by 625 plus 625. And this comes out to be 0.516. Q bar is 1 minus P bar. So we end up with 1 minus 0.516, which is 0.484. All right, we now have everything we need to find the formula for our z-test statistic. So I'm going to blow this up a little bit so I can write a little smaller. Z is equal to, we have P1 hat minus P2 hat divided by square root of P bar times Q bar divided by N1 plus P bar times Q bar divided by N2. Plugging this in, we have 0.472 minus 0.56 divided by square root of 0.516 times 0.484 divided by 625 plus 0.516 times 0.484 divided by 625. When we calculate this, we end up with negative 3.11. Okay, now we need to find the p-value. So to get the p-value, we're going to do normal CDF. This is a negative value because it's a left-tailed test, meaning we're going to do negative 10,000 up to negative 3.11, comma 0, comma 1. And so this will give us a p-value of 0.0009. All right, if you were doing this in the calculator, we would choose the 2 proportion z test. So when we enter this, we would be entering our x1, which is 295, our n1, which is 625, our x2, which is 350, and our n2, which is 625. Then we have to choose P1, and in this case, we're choosing less than P2. And then we go to calculate this. You will get exactly the same z value, negative 3.11, and then same p value, okay? Now, it gives you the p-value in scientific notation. Make sure that you don't tell me it's 9.2 times 10 to the negative 4th, okay? Or make sure you don't tell me it's just 9.2. Make sure you actually convert the times 10 to the negative 4th, so it's 0.0009. Remember, a p-value is a probability that's between 0 and 1. Okay, last step is to compare this to alpha. So our p-value is 0.0009 compared to alpha, which is 0.05. Our p-value is less than or equal to alpha, which means we reject the null hypothesis. So we have enough evidence to conclude the proportion of voters who registered was greater in group 2. And that's all I have for you.